Today we're going to use an intriguing result about just remainders that will help us solve this difficult looking problem. 16 is equal to 2 to the fourth, but notice this is congruent to 1, okay, modulo 5. And I'm just making this up. And the equivalent statement here that makes it more everyday is that 16 is equal to 3 times 5 plus 1. So this modular arithmetic is sometimes called remainder arithmetic. Okay, again, this is 16 is equal to 2 to the fourth. That's congruent to 1 mod 5 since 16 is equal to 3 times 5 plus 1. So you see the presence of this 1 here in the modular arithmetic form is all we're dealing with, really. Some people aren't really used to this notation, but it's really something that's you learn way back in grade school. It's just you're using different notation. Okay, now today we want to show that this infinite sequence comprised of terms of the form 2 to the n. Let's see, what the first one would be 1. If you put 3 in there, you get what, 5? Just writing down in the first few terms. If you put 4 in there, you get 16, you get 13, all right? So these are the first 3 elements in this set. And sometimes you can think of a sequence as a set of numbers. It's just a mapping from the natural numbers to the real numbers, okay? But we want to show that this infinite sequence has no multiples of 65. And we're going to kind of use this remainder idea. So now one thing that makes this a little more motivated is that you can be, these are separate problems, but you could show that this sequence has an infinite number of multiples of 5 and 13. Okay. Now, why is that interesting? Well, 5 times 13 is 65, right? 65 is equal to the 5 times 13 you see here. Right? Even though this fact, that it's not a hard proof really, has an infinite number of multiples of 5 separately and 13 separately, it has not a single multiple of 65. So let's get busy showing why that's not true. Now, here's the first important thing right here, I guess. Well, this nice little observation right here. Notice that 64 is what 2 to the 6 is, right? 64, 2 to the 6th equals 64. But 64 minus a negative 1, and that's what that's equal to 65, right? So we get that nice little result here that's going to help us out along the way because we are dealing with 2 raised to integer powers, okay? Now, the nice thing about congruence is you can treat them much like equalities, okay? Congruence is really divisibility converted into equality, sort of, all right? But if you square both sides, look, if you square negative 1, you certainly get 1. Now right here we multiplied through by 2 to the n. We multiplied this statement right here by 2 to the n on both sides to get this statement. And you use your laws of exponents, right folks? If you multiply this by 2 to the n plus 12 is what appears as this exponent. Then just like at regular equalities, we subtracted 3 from both sides. Now the very interesting thing about this is this intimates that this sequence has a period of 12. It repeats every 12 integer, so to speak, okay? And you guys famous, you remember like cosine has a period of 2 pi as does sine. And in general, what we mean by period is if you have a general function f at a plus p, where a is any real number, let's say, p stands for period, this is equal to f of a. So that means from a graphical point of view, it's going to look like itself infinite number of times for a period of size p. Okay, whoops, sorry, right out. That's f at a, sorry. So f at a plus p is equal to f at a. That's a definition of what we mean by period or periodicity. But so we've shown that our expression has a period of 12. And so it's enough to just check the remainders of the first 12. You could start anywhere and you're going to get all possible remainders. But notice that would be from 2 all the way down to 13. Y'all remember that's actually 12, right? If you go 13 minus 2 plus 1 is the way you have to think about this, right? That's equal to 12. Now, again, I bring that up because a lot of people get confused by this. Think about with 2, you have two numbers, right? But 2 minus 1 is 1, so you have to add 1, right? So notice we start at 2 and run all the way up to 13, and we know it's going to repeat itself. In other words, we know that 14 would be the same as n equals 2, all right? But now, y'all, I won't go through all the arithmetic, but notice we don't get any remainders of 0 here. No remainders of 0, which would be a requirement for something to be divisible by 65. No remainders of 0. Now, I may not have mentioned that up there, but it's an obvious fact, right? Like if you divide 21 by 3, you get 3 times 7 plus 0. You get a remainder of 0, right? Well, that's what modular arithmetic is. These are all remainders, 1, 5, 13. You guys can check the arithmetic here. I don't want to bore you with all the details, but I tried to write as much detail as I could. Like right here for 1,021, if you divide 1,021 by 65, you get a remainder of 46, all the way down. And you could, if you want to, you can use this fact 2 to the 12th is congruent to 1 to make these computations simpler. I didn't want to bore you with all that. But this isn't a matter of just using a calculator necessarily. You can use this fact 2 to the 12th is congruent to 1, or 2 to the 6th is congruent to -1 to do these computations also. Or you can just manually do a division. But the key aspect of this is that there's not a single remainder of 0 here. And these same 12 remainders that you see right here, 1, 5, 13, 29, 61, 60, 58, 54, 46, 30, 63, 64 repeat for, and you can start anywhere and you would get some sequence of this or partial of this, you know. But these will repeat in succession forever and ever and ever. But again, the key aspect is no remainder of 0, hence no term divisible by 65. Okay, y'all, that does it. I think it's a fun little proof. Talking about the notion of periodicity with these remainders. You may be reminded of irrational numbers that have periods of repetition in the decimal part. So that is all she wrote, folks. Hope you enjoyed.